And then tomorrow we're going to focus on limiting reactants. So here we go. The brief review of basic stoichiometry. And this podcast will be posted on YouTube if you guys want to refer back to it to help you with the homework. Okay. So stoichiometry, what it is, okay? The definition is the relationship between the quantities of reactants and products that are in a chemical reaction, okay? Not only are we interested in what kind of reaction will happen, we're interested in how much products we're going to get, how much of the reaction will be left over. That sort of thing in chemistry is, going to consume us the entire year, okay? So these are the kinds of questions we're going to answer in Chapter 5, okay? How much of one reactant do we need to react with something else, okay? How much of a product are we going to form? Will there be anything left over after the reaction is complete, okay? And et cetera, and et cetera. Tomorrow we're going to look at limiting reactants. Today is kind of like the slow pitch introduction, okay? So we're going to look at some examples to kind of refresh ourselves from last year and to kind of illustrate how this works, okay? Here's an example problem. This is on your note skeleton. What it says, okay, is the question is, what mass of oxygen in grams is required to react with 25 grams of glucose? Does anybody here know what glucose is? C6? H12? O6, there we go. That is blood sugar. Yes, exactly. Okay? And the question is what masses of carbon dioxide and water are going to be produced in that reaction. Okay? We're going to work this problem out, guys. Here's the steps. The first thing we need to do is write down the balanced equation for the reaction that is taking place. Okay? What are the two reactants? Glucose and oxygen. Okay, so here we go. We have glucose, C6, H12, O6. This is going to react with oxygen to produce products. What are the products going to be? Carbon dioxide and water. You guys know what kind of reaction this is? Combustion. In other words, a redox reaction. Do you guys know what process this is in your body? Yeehaw. There we go. Cellular respiration. That is absolutely correct. Okay. Here's the equation. What do we have to do now? We got to balance it. Okay. So in the products, okay, since we have 6 carbons over here, we got to have 6 carbons over there. Since we have 12 oxygen on this side, or 12 hydrogen rather on this side, we've got to have 12 over here. So we're going to slap a 6 there in front of our water, and now we have to balance the oxygen. Over here we have a total of 12 oxygen plus 6 is 18. Okay, so over here we got to have 18 oxygen as well. So we're going to put a 6 there in front of our oxygen. Does that balance? No? Did I make a mistake? It's okay? Okay, I like that. All right, there we go. Balance equation. Okay. Yeah, so we have 6 times 2 is 12 plus 6 is 18. Over here we have 6 times 2 is 12 plus 6 is 18. Oh, yeah. Okay. The second step, guys, is we're going to take the known masses of the reactants and we're going to change that into moles, okay? Then we're going to use mole ratios and we're going to figure out how much of the products we make. Okay, so here we go. There's several things we're looking for in this problem. We're looking for how much oxygen we need, okay? So how much of this do we require? How much of this is going to be produced, and how much of this is going to be produced, okay? The thing we know the given is we have 25 grams of glucose. Okay, so here's what I would do first. Let's change this glucose here into moles. How do I change the grams of glucose into moles? We're going to use the molar mass, okay. So what is the molar mass of glucose? Let's just kind of eyeball this. Each carbon's about how many grams per mole? It's about 12. This is going to be like a quick, we're out of pizza with a family calculation, guys. Okay, so we're going to say 12 grams per mole approximately with the carbon. On your homework, should you be so approximate? No, you should be exact, but here we're just going to be approximate. Okay, so each carbon's about 12, each hydrogen's about 1, each oxygen is about what? 16, okay. So 6 times 12 is like 72 plus 12, and then 6 times 16 of the oxygens is 96. What does that add up to? 180? I like when things are round like that. 180 grams per mole is the molar mass of glucose. Okay, so if we use the molar mass, so now we're going to change grams into moles using the molar mass. Okay, we have 25 grams of glucose. 1 mole has a mass of 180 grams. How many moles of glucose do we have? Calculate that baby. 7.2? 7.2 what? No, we don't. What am I talking about? What? Aha! All right, there we go. All right. 0.14, what's the next decimal? 138, okay, because here we go. We're going to throw back to sig figs here, guys. How many sig figs should this answer have? Should have 3, okay. So we're going to say 1.139 moles. I'm just going to call this gluc for the sake of abbreviation. Okay, so here we go. That's how many moles of my reaction I've got, okay? Now, everything else, I can use the number of moles here, right? Because this is kind of interchangeable with the mass, right? I can use that for the rest of my calculations, okay? So I want to know, okay? I'm just going to rewrite on this slide over here, my blank slide, the balanced equation. We have C6H12O6 plus 6O2 yields 6 carbon dioxide plus 6 water, okay? I know that I've got 0.139 moles of glucose, okay? Now, I want to know a couple things. I want to know how much oxygen will it take to fully react with that, and then I want to know the masses of the product. So this problem is kind of like 3 different parts, okay? To figure out how much oxygen, the mass of oxygen it takes to react with the glucose, what am I going to do? Let me call on a victim. Use the what? Use the mole ratio. Ruben, how would I do that? 6 moles of oxygen over 1 mole of glucose. Ruben, where'd you get that from? We got that from the balanced equation, yes. Oh, no, that's right. This comes from the balanced equation, right? Because in the balanced equation, we see there's 6 O2s for every 1 glucose there is. Okay, there we go. Now, the next step, right? I changed moles of glucose now into moles of O2. What do I do next? Change it into mass. Chart and multiply by the grams of oxygen per mole, which is the molar mass of O2. In 1 mole of O2, guys, how many grams are there? 32, right? Because this is O2, and each oxygen is 16 times 2 is 32. So there we go. 0.139 times 6 moles of O2 for every mole of glucose times 32 grams per mole of O2. And there we go. That's how we're going to get the answer. Okay, what is the mass of oxygen that we get at the end? What's that? 26.688. Okay, so we want to round that to the right number of sig figs. What would that be? Like 26.7 grams? Okay, there we go. Of O2. That's the amount of oxygen that it takes to react with the glucose. Give me a thumbs up if you guys see how we got that. That jogging memories from last year? Okay. If I want to know how much carbon dioxide I'm going to get here into the products, okay, let me call on a victim to walk me through that. How about Janice? How would I figure out how much carbon dioxide gets produced? Okay, do the same way, right? We're going to start with the given, right? 0.139 moles of glucose. What would I do next? Six moles of carbon dioxide for every 1 mole of glucose. And then what? Times the molar mass, right? Okay. And if we just do that in our heads really quick, okay, each carbon's 12, each oxygen is 16, so it's like 44 grams in 1 mole. Keep in mind, guys, I'm chopping off the decimals here for the sake of brevity, but when you guys do this for homework, don't do that. Be as exact as possible. Okay, so our moles of carbon dioxide cancel out, our moles of glucose cancel out. We have grams. If we go through and calculate it, what do we get? 36.7 grams of carbon dioxide. And there we go. Yeah. Do you guys think you could do the same thing for water? Yeah, okay, absolutely. All right. So we'll skip that part. All right. Let's do one more, okay? This is a basic stoichiometry problem, right? Where we took the given here, we changed that into moles, and figured out how much of this we needed to react and how much of our products we make. Okay, we're going to do one more, okay? Here it says a 1.24 gram piece of phosphorus, which has a formula of P4, reacts completely with chlorine gas to give phosphorus trichloride. What do you think the formula of phosphorus trichloride is going to be? PCl3, there we go. The question is, what mass of chlorine is required for the complete reaction? What mass of phosphorus trichloride is produced? Okay, so if we go through and do the calculation, if we want to do the problem, the first thing we have to do is we have to write down the balanced equation. One reactant is P4. What's the other one? Cl2 has chlorine gas. This is going to react to give PCl3. What do we have to do to balance that equation? Put a 4 in front of that. And then what? And then a 6 in front of that. Okay, so 6 there in front of my chlorine. There we go. That is the balanced equation. That is totally correct. Okay, now here we go. There's two things we need to find. Okay, it's asking what mass of chlorine is required for the complete reaction and what mass of this is going to be formed. Okay, so in the problem, we're going to start with the given, which is 1.24 grams of P4. Okay, the first thing is we're going to change that baby into moles. Okay, so 1 mole of P4 has a mass of X many grams. Do you guys know off the top of your head what the molar mass of phosphorus is? Wow, all right, 31 approximately. Okay, so if we do that, it's going to be like 124 grams per mole. Something like that, right? Okay, how many moles do we have then? It'd be like 0.01 or something like that. Okay, well, we can keep going, right? We don't have to simplify already. Okay, if we want to change this, okay, now we got moles of P4. We could change this directly here into moles of chlorine required to react. We're going to multiply now by a mole ratio. What's the mole ratio of chlorine to phosphorus in the balanced equation? 6 to 1. So 6 moles of chlorine for every 1 mole of P4. Okay, P4 here goes away, grams goes away. We're going to have moles of chlorine. The last thing we want to do is we're going to multiply now because we're interested in the mass of chlorine. Okay, we're going to multiply by the molar mass of chlorine. 1 mole of chlorine gas has a mass of approximately 70.90 grams. If we go through now and do the calculation, what do we get? What's that? 4.25 grams of Cl2. Something of that nature. That looks right, okay? Now if we want to do something analogous to find the mass of phosphorus trichloride produced, could we do that too? Yep, we could. We could start from the same point, 1.24 grams of P4. Okay, we're back. For those of you guys in internet land, here we go. So if we're going to find the mass of phosphorus trichloride that is produced in the reaction, we'd start again with the given 1.24 grams of phosphorus, or we can start with the number of moles, either way. Change that into moles, so 1 mole of phosphorus, P4, has a mass of 124 grams, okay? If we look at the mole ratio here in the reaction, okay, we see that 4 moles of phosphorus trichloride, PCl3, is produced for every 1 mole of P4 that reacts. Again, now last we're going to multiply by the molar mass. I don't know what that is off the top of my head, so I'm going to have to calculate it, okay? Phosphorus is, if we round, about 31 grams per mole, okay? Each chlorine is like 35.45, so you can take that and multiply by 3, okay? So this is approximately 137.35 grams in every 1 mole of PCl3, okay? That's going to cancel out. Moles of P4 cancels out. Grams cancels out, okay? And now we're going to be left with mass of phosphorus trichloride. If we go through and do the multiplication, guys, 1.24 divided by 124 times 4 times 137.35 gives us 5.49 grams of PCl3 will be produced in the reaction. Okay, there we go. Now, the one last thing I want to just bring up here really fast is something called percent yield, guys. If we go back here to this reaction, this is something chemists do every day. We want to calculate how much of something we can produce during a reaction. Now, the assumption in this problem is that this reaction has gone all the way to completion, and we get all the products out that we possibly can, okay? This right here, what we calculated, this amount of product that we could produce in the reaction, this is called the theoretical yield, okay? This is the maximum mass of phosphorus trichloride that can be produced in the reaction. However, we don't always recover the entire theoretical yield from the reaction. For whatever reason, sometimes the reaction does not go to completion. Maybe we don't obtain or separate all the products from the vessel we're conducting the reaction in. Okay, so to gauge how well we did, basically, we will calculate something called percent yield. Okay, so say for the sake of argument that we did the reaction that we described in the previous example, but we only get 5 grams of the product at the end. We only isolate 5 grams of the product, okay? Let's calculate the percent yield. Here's how you figure out the percent yield, okay? There's a formula. Percent yield, as you remember from last year, is going to be your actual yield, okay, This is, by the way, the actual yield, what you actually got out of the reaction, okay? Divided by the theoretical yield times 100%, okay? In this case, the actual yield was 5 grams. The theoretical yield, the maximum we could possibly make, was 5.49 grams, and we're going to multiply the quotient by 100%. If we plug that into our calculators, you should do that with me, okay? We get 5 divided by 5.49 times 100, and this is pretty good, actually. We get 91.1% yield. And guys, if you're doing a reaction and you get 90% yield, that is fantastic. I've only actually, in any reaction I've ever done, gotten 90% plus yield a couple times, okay? This is usually about as good as you can do, just because you don't always isolate all your products, okay? So guys, that is the end of the notes for today. Tomorrow we're going to talk about limiting reactants. I hope you guys bring your A game, because limiting reactions are tough, and they're something you're going to have to deal with every time you do a stoichiometry problem for the rest of the year in AP Chemistry. So until tomorrow, guys, have a good night. I will see you later. Goodbye.